How do you design cooling systems to avoid thermal runaway? When it comes to designing cooling systems that prevent thermal runaway, the focus is on managing heat effectively. This is essential in applications like batteries, where excessive heat can lead to dangerous situations. Let's break down the key components of a successful cooling system. First, it is crucial to understand that thermal runaway happens when the heat generated exceeds the system's ability to dissipate it. This leads to a rapid temperature rise. Therefore, the cooling system must efficiently remove heat and prevent it from spreading to nearby components. One effective method is to use active cooling techniques. Forced air cooling, liquid cooling, and immersion cooling are popular options. Liquid cooling is often more efficient than air cooling, especially in high-power applications. However, it can be more complex and costly. Immersion cooling, where components are submerged in a special fluid, provides excellent heat removal but comes with its own engineering challenges. In addition to active cooling, incorporating thermal insulation is vital. Using materials like aerogel or fire-resistant foams can create barriers that prevent heat from spreading. These materials should have low thermal conductivity and be resistant to burning or melting. Some even form a protective layer when exposed to heat, adding an extra layer of safety. Temperature monitoring is another key aspect. Strategically placing temperature sensors allows for real-time data on component temperatures. This information enables dynamic control of the cooling systems, ramping up cooling efforts when temperatures rise. Implementing thermal management software can help monitor temperature, current, and voltage, detecting early signs of thermal runaway risk. Designing for containment is also essential. Physically separating cells or modules with thermal barriers allows heat to dissipate and reduces the chance of thermal runaway spreading. Fire protection coatings on casings can minimize heat transfer through the structure. Lastly, ensure that cooling systems are isolated from potential thermal runaway events. This means that even if part of the system fails, the cooling circuits should remain operational. Providing enough cooling capacity to absorb heat generated during a runaway event is also critical. These principles are applied in various practical applications, such as electric vehicle battery packs and stationary energy storage systems. Layered thermal barriers, active liquid cooling, and sophisticated monitoring systems work together to maintain safety and performance. Designing cooling systems to avoid thermal runaway requires a combination of active heat removal, passive thermal insulation, real-time monitoring, and protective containment strategies. These elements work together to keep temperatures safe and prevent rapid escalation.